The overall goal of the following experiment is to purify magnesium borohydride, a porous complex hydride and high-density hydrogen storage material, using supercritical nitrogen. This is achieved by first soaking a sample of magnesium borohydride in compressed liquid nitrogen in the near critical region of the phase diagram at -163°C and 20 bar, where its high fluid density is indicative of a high solvent power toward target impurities such as diborane and N-butyl species. As a second step, the liquid nitrogen is heated and compressed into the dense supercritical region of the phase diagram at -123°C and approximately 100 bar. Next, the supercritical nitrogen and any dissolved species can be extracted from the sample by slowly reducing the pressure to vacuum at -123°C, thereby circumventing the liquid-to-gas phase transition, where surface tension effects can lead to poor extraction of the target species. The results show that after iterative supercritical nitrogen drying treatments, the gaseous decomposition products of magnesium borohydride only consist of hydrogen, based on temperature-programmed decomposition coupled with infrared spectroscopy.
The focus of our research activities is the material science connected to the storage of renewable energy. Since the beginning of our pioneering research on complex hydrides as hydrogen storage materials, the synthesis of borohydride compounds has been a challenge. Pure compounds are difficult to produce, but essential for scientific investigations.
Purification methodologies can help answer key questions in the field of solid-state hydrogen storage, such as what role impurities play in the decomposition reactions of complex hydrides. The answer remains complicated.